And our today's topic is annihilators. The concept of annihilator is connected to the idea of orthogonality, or you can say that the definition of annihilators depend upon the idea of orthogonal vectors. So let's come towards the formal definition of an annihilator. For that, suppose we have H as a Hilbert space. You all know what is a Hilbert space. A complete inner product space is called a Hilbert space. What is a complete inner product space? An inner product space in which every Cauchy sequence is a convergent sequence is called an complete inner product space or a Hilbert space. So suppose we have a Hilbert space or complete inner product space H, and we take a subset A of this H. A is a subset of H. Then we say that some element small x of H inside X, this element X is said to be annihilator of A, or we can say that this small element X is orthogonal to the whole set A if this X is orthogonal to every element of A. Previously we studied the orthogonality between two elements, but here we are studying the orthogonality of an element towards a set. X is an element of the bigger set H, the inner product space H, and we say that this X is orthogonal to the whole set A only if and if only that the inner product of this X to all the elements of A is equal to 0. Then we say that this element is orthogonal to the whole set, or we can say that okay, this is the definition of orthogonality. We can say that X is orthogonal to A if X is orthogonal to the whole set A or every element of A. So this was the definition of an element that is orthogonal to a subset A of H. Now we are coming towards annihilator. For example, we have a Hilbert space H and there is a subset A of the Hilbert space H. Then the set of all such vectors inside the bigger set H is said to be annihilator, which are orthogonal to the set A. Explaining this definition, what I said is H suppose is a Hilbert space, A is a subset of this H. Then we say that, for example, X is an element as we described here that is orthogonal to every element of the A. Or we can say that this X is orthogonal to the whole set A. Right? We have written over here that X is orthogonal to the whole set A. Now if we find another element of the same kind, for example a or small b, which is orthogonal to the whole set A, similarly we are finding many more elements like this. The set of all such elements is called annihilator of A. It's called what? It's called annihilator of A. Then they say that the set of all such vectors of H which are orthogonal to A is called the annihilator of A and is denoted by A orthogonal like this. Or we can say that A annihilator consists of all those elements X inside H which are orthogonal to A. For example, X is an element which is orthogonal to A. Similarly, another element Y which is orthogonal to the whole set A, and similarly many more elements. So the set of all such elements which are orthogonal to A is called the annihilator of A. Therefore, the annihilator of A is denoted by this thing, A orthogonal. Also, the annihilator of A annihilator, I mean the double orthogonal we are taking, is denoted by this one. For example, this is annihilator of A and we want to find the annihilator of this set which is also annihilator itself, then that is denoted by A double orthogonal. Therefore, this A double orthogonal consists of all those elements which are orthogonal to this set, not A originally. This set will contain all those elements which are orthogonal to this set, of course, as per definition. So it will contain all those elements which are orthogonal to annihilator already. Now looking to that definition, we can see that what are those elements which are orthogonal to this set 0. For example, we have a set Hilbert space H and we take its subset, that is a singleton set containing only one element 0, and we want to find the annihilator of this singleton set, right? 0 annihilator. You want to find that, so it will contain all those elements which are perpendicular, which are orthogonal to 0. So of course we know that the inner product of every element of H will be perpendicular, will be equal to 0. For example, if I am taking any element x, y, z, whatever, and taking its inner product with 0, the result will be 0. This means that every element of the H is perpendicular to 0. This means that the orthogonal or the annihilator of 0 contains the whole set H. Therefore we can say that the annihilator of 0 is equal to H. Similarly, if I am taking this H, the whole Hilbert space, and I want to find its annihilator, then there is no such element which is orthogonal to the whole set. For example, I'm sorry for the interruption. Okay, so I claim that there is no such element in the set H which is orthogonal to the whole set H itself. For example, if I take a random element x from this set and I want to check if this is orthogonal to the whole set or not. Okay, this small element x can be orthogonal, might be orthogonal to every element of the H, but it can never be orthogonal to itself, because when we take the inner product of an element to itself, it becomes norm, and norm is always greater than or equal to 0, or you can say by definition we have written that this is always greater than or equal to 0. We have said this in the definition of inner product. So if this is so, this means that an element cannot be orthogonal to itself. If an element cannot be orthogonal to itself, this means that it cannot be orthogonal to the whole set, because the whole set contains itself, the set X itself. So if X is not orthogonal to itself, then X is not orthogonal to the whole set, because X lies inside H. It means that if instead of X, whatever whatever element we are taking from the set H, that element, for example Y, will not be orthogonal to the whole set H. Why? Because Y is also contained in H, and if it is contained in H, it is not orthogonal to itself, so it is not orthogonal to the whole set H. So there is no such element except one element, and that element is 0. Why? Because we say that 0 is orthogonal to every element in a set H. Therefore, the orthogonal or the annihilator of H contain only one element 0, and the annihilator of 0, a singleton set 0, contains the whole set H. Now let's prove this theorem that says, suppose we have a Hilbert space H and A is a subset of the Hilbert space H. Prove that A is a subset of A double orthogonal, or annihilator of A annihilator. So to prove this, we will be choosing some element from this set, and we will prove that that element also belongs to this set, and hence we will get our result. So suppose an element from here, so X is an element from the left hand side, and we want to prove that X also belongs to this one. Okay, if X belongs to A, then xy is equal to inner product of xy is equal to 0 for all y belong to A, orthogonal, because whenever y belong to A orthogonal, so it will have its orthogonality property with the elements of A because of this definition. Okay, so therefore if x belong to A satisfy this property, that inner product of xy equal to 0, then we can say that x belong to annihilator of A, and if x belongs to annihilator of A, then definitely it will belongs to the annihilator of A annihilator, because when an element x is orthogonal to A annihilator, it means it belongs to the annihilator of A annihilator. So we have chosen x from A and proved that x belongs to A double orthogonal. This means that A is a subset of annihilator of A annihilator.